Good morning, dear students. I am Dr. Jeevan Godke, Department of Physics, Padma Bhushan Dr. Vasantrada Patil Mahavidyalaya, Tasra. Today I am going to discuss about application of Schrodinger's wave equation. In these chapters, we will discuss how Schrodinger's wave equation is applied to different physical systems, such as motion of free particle in a box, particle in potential barrier, particle in square well potentials, and to determine, derive its energy eigenvalues and eigenfunctions associated with them in different quantum conditions. Let us consider first point, particle in a rigid box in one dimension. In this case, we have to calculate energy eigenvalues and eigenfunctions associated with the particle during its motion in one-dimensional rigid box. We know that in quantum mechanics, a rigid box means a system in which the potential energy is a zero within a closed regions and infinite everywhere. Consider particle moving inside a rigid box along a x direction. Particles moving inside a rigid box along x directions is as shown in this figure. The particle is bouncing back and forth between the walls of a rigid box. Hence, there is no existence of particle outside the box. That is, the potential energy of particle becomes infinite outside the box, while inside the box the potential energy of particle is zero. That is, between x is equal to 0 and a, its value becomes a 0. Therefore, we can write boundary conditions for potential energy, and its function is phi is equal to 0 for x lies between 0 to a, and the value of this v is equal to infinity for x less than equal to 0 and x greater than equal to a. To calculate energy eigenvalues and eigenfunctions associated with particle during its motion in one-dimensional rigid box. Consider Schrodinger's time-independent equation in one-dimensional case is dou square psi divided by dou x square plus twice m divided by h cross square e minus phi psi is equal to 0, equation number 1. We know that inside the box, its potential energy of particle V is equal to 0. Therefore, our equation, this one becomes dou square psi divided by dou a square plus twice m divided by h cross square e psi, where this V is equal to 0. Hence, we get this equation. In this equation, consider twice me divided by h cross square is equal to k square, equation number 2. Hence, this above equation becomes dou square psi divided by dou a square plus k square psi is equal to 0, equation number 3. Then we have to write its solution. Solution of this differential equation is psi is equal to a sin kx plus b cos kx, equation number 4. We have to solve these equations and to determine the values of constant a and b by using the boundary conditions. The value of this wave function psi is equal to 0 at x is equal to 0, and also the value of this psi is equal to 0 at x is equal to a. Hence, from our equation, that is equation number 4, we have to write by using this first boundary conditions, psi is equal to 0 at x is equal to 0. Therefore, this psi is equal to 0 is equal to a sine k, x becomes 0, plus b cos k, x becomes to 0. This cos 0 is equal to 1, sine 0 is equal to 0. Therefore, from this equation, we get b is equal to 0. Therefore, our equation this 4 becomes psi is equal to a sine kx. Equation number 5. Then by using second boundary condition, at x is equal to a, psi is equal to 0. Hence, this equation 5 becomes 0 is equal to a sine ka. To solve these equations where a is not equal to 0, therefore this sine ka is equal to 0, where ka is equal to pi, 2 pi, 3 pi, n pi. That is, this ka is equal to n pi, where n is equal to 1, 2, 3. Rearranging these equations, we get equation number 6, that is k is equal to n pi divided by a. Squaring on both sides, this k square is equal to n square pi square divided by a square, equation number 7. Consider equation number 2, k square is equal to twice me divided by h cross square. Comparing this equation to, that is both equation number 2 and equation number 7. That is from this equation 2 and 7, we write twice me divided by h cross square is equal to n square pi square divided by a square. Rearranging this equation, we write this e is equal to n square pi square h cross square divided by twice m a square. That is, this energy E is equal to n square h cross square pi square divided by twice m a square. From these equations, we write the energy eigenvalue of particle confined inside the box. For nth states, its energy eigenvalue becomes En is equal to n square h cross square pi square divided by twice m a square, equation number 8. That is, this is the resultant equation of an energy of particles, particle confined in one-dimensional rigid box having length a. Then we will write eigenvalues. That is, from this eigenvalues, then we have to write its eigenfunctions. This is the eigenvalues, energy eigenvalues. Eigenfunctions of particle confined in one-dimensional rigid box. We have to write from this equation psi is equal to a sine kx, where this k is equal to n pi divided by a. Therefore, the wave function psi, this wave function psi for nth state, this is the thing with the energy for nth state, then psi wave functions for nth state is equal to a sine k. K is nothing but this one. Okay, therefore n pi x divided by a, that is the wave function psi is equal to, wave function psi is equal to a sine n pi x divided by a, This is the equation number 9. Thus, equation 8 and equation number 9 represents the equation of an energy eigenvalues and eigenfunctions of particles or nth state. Okay, thank you.